which has escaped my attention for the past 40 or 50 years. I do have long-time NCAR connections, though. I did my PhD research at University of Michigan as even a theoretician at that time, and I did it running the NCAR computer remotely from Michigan. At the time, it was the CDC 7600. Does anybody remember that? This was pre-Cray, but that was what I used for my thesis. And then when I got out of Michigan, I came to NCAR for 2 years. I was in the advanced study program from 1979 to 1981. I worked with Ray Roble, who I think many of you probably know. And was Ray in HAO?
Not at that time.
Okay. Yeah, I've forgotten the divisions. But anyway, I worked with Ray for 2 years. And then I actually had an opportunity to stay here. Paul Crutzen invited me to stay on. And this was before Paul became really famous from getting his Nobel Prize. But I had gotten an invitation from Jim Pollack out at NASA Ames to go do planetary science out there, planetary atmospheres. And that was what I was really interested in. And it sort of bears on what we're talking about at this meeting, you know, that I wanted to go to Ames because I was interested in NASA things, and I felt like that would be a better place to do that than staying at NCAR. But that said, we use lots of the same tools that people do here. Many of the tools that I use in my own research, I first developed through connections here at NCAR. Let me give you an outline for the talk here. My talk is nominally on habitable zones, but I find that most of the questions I get are not on the details of the calculations, they're on the underlying premises. So I'm going to start out and talk briefly about the basic requirements for life. Part 2 is on the definition and boundaries of the habitable zone, which is the part that I actually work on. And part 3 is important recent developments, most of which have been mentioned already by the speakers yesterday and today. So I can skim through this actually pretty quickly. And let me encourage you, if you have questions as I go along, feel free to ask them. I don't mind being interrupted during the talk here. All right, requirements for life. I'm going to list 4 here, 3 of which most people agree on here. First is that I think you need a planet with a liquid or a solid surface. That means no gas giants. And here I'm less of an optimist than Carl Sagan. If you ever read Cosmos or watched the movies, he had these giant there are actually videos of these giant floaters in Jupiter's atmosphere that adjust their altitude by changing their internal pressure, sort of like some fish do in the water column. They've got air bladders and can stay at the same pressure temperature level. But life to originate, we all think it originates in single-celled form, and you can't do that as a single-celled organism. So most people don't think you can originate life on gas giants. You need a thermodynamic free energy gradient to drive metabolism and growth. I'm not going to talk much about that. Stellar radiation is the basic free energy source for most surface life on Earth, but there's lots of organisms living at hydrothermal vents that don't depend on that. That's not too relevant to what we're talking about today. Availability of carbon and other bioessential elements, SNOPs in the lingo. Some people will question that. Steve Benner's a well-known biochemist who likes to think out of the box. And I used to read a lot of science fiction when I was growing up, and science fiction authors, have long been into silicon-based life. Silicon's right below carbon in the periodic table and can do some of the same things chemically. But silicon forms really strong bonds with oxygen and forms things we call rocks. And then once you make rocks, it's difficult to break them apart. So most of us don't think that there really is silicon-based life. Then the 4th requirement, which has already come up in Eric's talk earlier, is liquid water. And this one is more controversial. We already had a brief discussion about Titan. There's liquid methane lakes on the surface of Titan. There are people who want, we've been Titan with the Huygens probe and looked a little bit. Jonathan Lenine wants to go back there with a boat someday. And I should mention there is a mission going back to Titan with a helicopter. That's Dragonfly. That's Libby Turtle at APL is the PI on that. That's a funded mission now. So Titan's really interesting, and maybe there's life in the methane lakes of Titan. I'm personally skeptical, but that's a fascinating place to go, and we'll find out the answer to that question. For extrasolar planets, things like that are less interesting, I think, because all we're going to get if we, what we really want is single pixel resolution of a planet's atmosphere. And we've just heard how difficult that is to get. At the end of my talk, I'll come back to it. There are LUVOIR and HABEX are these proposed missions that would do that for us. But you're not going to be able to, for instance, Titan, we've been looking at Titan with telescopes for hundreds of years, and you can't tell a thing about the presence or absence of life on Titan's surface, right? So I think if we're going to see and interpret these exoplanets in terms of life, we're going to have to look for something fairly close to what we have here on Earth. The other thing that I'll remark that I would make is that subsurface water is also very important for planets in our solar system. Most of NASA's astrobiology program is actually focused within the solar system, and a large part of it is on Mars. There could be subsurface life on Mars today. There's also Europa and Enceladus, which have subsurface oceans. Cassini has flown through the plumes of Enceladus, and there's the Europa Clipper mission going back, so there's lots of interest. Again, these are objects within the solar system which we can explore with planetary missions, and so we can determine eventually whether there's life in these subsurface oceans or maybe in the deep subsurface of Mars. But if you're doing exoplanets, in the foreseeable future, we're not going to be flying there and doing those observations. So it's single pixel resolution. As Eric already said previously, you need life to be present at the surface so that it can modify the atmosphere in a way that can be detected at modest spectral resolution. And so you need that's the rationale for surface liquid water. Right? And this leads to a definition of a parameter that the exoplanet astronomers use. It's called eta sub Earth. It's the fraction of stars that have at least one rocky planet in their habitable zone. It's very similar to the third term in the Drake equation. More people are familiar with that. That term is n sub e, the number of Earth-like planets per planetary system. And the only difference between eta sub Earth and n sub e is that eta sub Earth is constrained to be between 0 and 1. N sub e can be greater than 1. In fact, as Eric already said, n sub e for the present solar system would actually be 2 because Mars is nominally within the habitable zone along with Earth. Why do we care about eta sub Earth? Well, these big missions, the direct imaging missions, which I'll come to at the end of my talk, they need to design parameters. And so eta sub Earth tells you something about how big that telescope needs to be. If every star out there has a potentially habitable planet, you only need to survey so many of them. But if the eta sub Earth is small, then you need to look at more stars and you need a bigger telescope and maybe more time, right? And the other bullet on here is that we should be conservative when calculating eta sub Earth because we don't want to undersize these big telescopes that we're hoping to build. Okay, so that brings me to the definition and boundaries of the habitable zone, which, as I said, is the part that I actually have worked on. And I found out just recently that I'm guilty of misquoting the origin of the term habitable zone. I've been misquoting it for about 25 or 30 years. I thought it was invented by Sushu Wang in 1959, who wrote a paper and he used the term habitable zone. But Ralph Lorenz gave a talk at the 2018 DPS meeting, Division of Planetary Sciences, that I missed. I wasn't there. However, my colleague Jason Wright at Penn State dug up his abstract and found out what Lorenz's talk was on. The term habitable zone was actually used by Walter Maunder in this book, Are the Planets Inhabited, in 2013. And we've already heard some about the Maunder minimum at this meeting. Jack Eddy coined the term, and in a 1976 paper in Science, which, by the way, I looked up the citations on that. There's about 1,300 in Web of Science and 2,400 on Google Scholar. So this is one of the most highly cited papers. I also looked up the Wikipedia article on the Maunder Minium and Jack Eddy. Eddy was employed by HAO until 1973. And then, according to Wikipedia, there were budget cutbacks then, and he was let go. I think also partly because he got interested in historical research. It wasn't just the Maunder Minimum. He was doing Indian medicine and artifacts and things. Anyway, so by the time he wrote his paper, he was no longer associated with HAO. But then he went around the world and gave talks all over the world on this. And in fact, he was still talking about it in 1978 or 1979 when I got to NCAR, because I distinctly remember hearing him give a talk about the Maunder Minimum when I was first here. And here's a picture of Edward Maunder and Annie Maunder taken from the web. This is the quote that's in the Maunder's book Jason Wright found. "Can we expect that in more cases than 1 in 100, there will be a planet in the habitable zone, fulfilling all the other conditions of habitability of size, mass, inclination of axis, circular orbit, and rotation?" So I've missed that for a long time, but I won't miss that in the future. The other thing I'll say about Wikipedia is, I don't know who wrote the article there, but Maunder is described as a second-rate scientist there, who and that the credit should have been given to Sporer. But Eddy apparently didn't. He liked the alliteration in Maunder Minimum. It sounded better to him. This is according to the Wikipedia article. So I don't know how people feel about that, but somebody could edit that if they don't like that particular perspective. Okay, back to the habitable zone. I became aware of this back when I was a graduate student because there were 2 papers written by Michael Hart, who was a planetary scientist at NASA Goddard, and he used the term habitable zone. In fact, he did something which I think was very good. He defined 2 different types of habitable zone: an instantaneous habitable zone, which is the region around a star that remains, in which liquid water can be maintained at some instant in time. But then he also defined the continuously habitable zone, or CHZ, which is the region that remains habitable for some particular time period. All stars get brighter as they evolve, M stars very slowly, but earlier stars much more rapidly. And so the continuously habitable zone is a relevant concept in the search for life. For the solar system, we usually use 4.6 billion years. Yeah, because that's the age of the solar system, right? Let me just, well, I'll come back to that in a moment. Hart was very much a pessimist on this. Before I do, though, I should say there's some controversy about the name habitable zone. There are other names for it. There are people that don't like the name habitable zone. Harlow Shapley talked about the habitable zone in a 1953 book, but he didn't call it that. He called it the liquid water belt, which actually has not much ring to it. I think that's probably why that didn't stick. Strughold called it the ecosphere in that same year. Lynn Margulis used to call it the Goldilocks zone. We've heard that term here already at the meeting. Francois Forget over in Paris, he's the head of the LMD group. He called it the hunting zone at a meeting fairly recently. And he called it that because that is the region in which we would hunt for habitable planets. But I was at a SETI meeting in Green Bank this past summer. They're interested in the search for extraterrestrial intelligence, and if you call it the hunting zone, it has bad connotations. So I think that's. And then Elizabeth Tasker, who's this young astronomer who's now at ELSI, the Earth and Life Science Institute in Japan, has a book out, and she calls it the temperate zone. We just heard from Eric that there's problems with that too, because the habitable zone is actually much wider than the temperate zone. And the temperate zone doesn't even describe the whole Earth, right? It's just part of Earth. So I'm personally quite happy with the term habitable zone. All right, back to Michael Hart's calculations. His papers came out in 1978. That was about the habitable zone around the Earth. And then in 1979, he extended this simple model to other stars. And he was very pessimistic. So he concluded that the instantaneous habitable zone, the instantaneous the CHZ around our own sun is quite narrow, going from about 0.95 astronomical units on the inside, where he got a runaway greenhouse in his model, to 1.01 AU on the outside, where he got runaway glaciation, and his models could never recover from runaway glaciation. That's a problem, right? Because we just heard Eric mention that there have been snowball Earth episodes on the Earth, which are pretty well documented, so we think that the Earth has escaped from runaway glaciation. And then the second paper, Hart applied his model to other types of stars, and the model was tuned for our own solar system, and so it didn't work at all for these other types of stars. So he concluded that Earth might be the only habitable planet in the entire galaxy. And then there are pessimists everywhere, including in the astronomical community, and you can still find introductory astronomy textbooks that quote that result and say that life is very rare. Well, I was much more optimistic. I was a big fan of Carl Sagan when he was around, and Sagan was the ultimate optimist, right? He thought that there was probably life everywhere. So this was one of the things that motivated me during my graduate career. I was really disappointed to see that this was the state of the art here, and I wanted to see whether there might be ways around this argument that Michael Hart had constructed. All right, so I already said this. Hart concluded that a fully glaciated planet couldn't deglaciate. The reason he concluded that, I used to think it was because he didn't have the carbonate-silicate cycle feedback, which I'm going to talk about in a minute. But he did have a crude feedback in there. He chose a greenhouse model, which was very weak. There were about 6 or 7 different models of the greenhouse effect. Hart, if you look him up, I think he had an agenda. He was, he's been quoted by creationists, so I think he wanted to show that there was, that the Earth was unique. I think that's a bad way of criticizing someone's science, but he picked a model that had a very weak CO2 greenhouse effect, and with that model, he couldn't deglaciate from snowball Earth conditions. There is a feedback, which I've worked on and off for a long time, and that has to do with feedbacks on atmospheric CO2. If you know anything about Earth's climate, the 2 main greenhouse gases are water vapor, which is the best greenhouse gas, and CO2, which is second best. Water vapor is near its condensation point, though, and so it participates in feedbacks, some of which Eric Wolf talked about just now. CO2 also participates in feedbacks, but on short time scales, it's a climate forcer. We're forcing it right now with global warming. On long time scales, there's actually on glacial to interglacial time scales, there are positive feedback loops. On really long million-year time scales, there's a very strong negative feedback loop here, which Eric mentioned. It has to do with the carbonate-silicate cycle, which is also called the inorganic carbon cycle. People are mostly familiar with the organic carbon cycle, which is photosynthesis going in one direction and respiration and decay going in the other direction. And that recycles all the CO2 in the atmosphere on a time scale of about 10 years, so it's very rapidly. But that's largely in balance, and in fact, it has to be in balance because otherwise the oxygen content of the atmosphere would fluctuate wildly. So that cycle we think is controlled by redox balance. The carbonate-silicate cycle has no redox changes. You start over here on the left. CO2 dissolves in rainwater, gives carbonic acid, which is a weak acid, strong enough to dissolve silicate rocks and carbonate rocks. It's the silicates we care about here, represented by the simplest calcium silicate mineral, CaSiO3. Real silicates are more complicated. You weather that, you form dissolved calcium ions and bicarbonate and dissolved silica. Those ions are carried by streams and rivers down to the oceans, where various organisms make shells out of calcium carbonate. And then that calcium carbonate gets deposited. Well, most of it, when the organisms die, they fall into the deep ocean. Most of the calcium carbonate dissolves because the deep ocean is more acidic than the surface ocean, but in some places you form carbonate sediments, and then we know from geophysics that the seafloor is not sitting there. You have plate tectonics, And you got spreading at the mid-ocean ridges and subduction at certain plate boundaries. And so those carbonate sediments are carried down, and you have a process called carbonate metamorphism that goes on that reconstitutes the silicate minerals and releases CO2 into the atmosphere. So that process is slow. For Earth today, it's about 500,000 years. You can think of the CO2 in the combined atmosphere-ocean system is the relevant quantity here. That total amount of CO2 is recycled by this process in about 500,000 years on the modern Earth. So it's way too slow. And I should say that the feedback is that if you get too cold, then say you go into global glaciation, the weathering side shuts down because weathering takes liquid water. These reactions between gaseous CO2 and dry silicate minerals just don't go at Earth-like temperatures, right? So if you shut down the water cycle, then weathering stops, but volcanism continues. CO2 builds up into the atmosphere until you get enough greenhouse effect to melt the ice, right? And most of the time, the Earth doesn't freeze over. There's only 2 or 3 documented snowball Earth episodes in Earth history. Most of the time, there's a negative feedback that if the climate gets colder, weathering slows down, CO2 builds up. Conversely, if the climate's too warm, weathering speeds up, CO2 goes down. So it's a buffer on the Earth's climate, right? And so Eric already mentioned the faint young sun problem. That we think is a large part of the answer to the faint young sun problem. The sun was 30% less bright when we started, at 4.6 billion years ago. There's pretty good evidence that the Earth was not frozen during the first half of its history. And so why was that? Well, CO2 is probably a large part of the answer. There is a caveat to that, which some people have been aware of for a couple of decades, but I didn't become aware of until 5 or 6 years ago, that if you have planets that near the outer edge of the habitable zone, if they either have low volcanic outgassing rates or they're getting less stellar illumination than the Earth, you can get limit cycling going on where you do go snowball and melt off regularly. So this was first shown by a Japanese scientist named Tajika way back in the early 2000s. I reviewed some of those papers, and I never paid much attention to it because he was writing about the early Earth, and he said if volcanic outgassing rates were 10 times lower on the early Earth, then the Earth could have done this weird behavior. And so, it looked correct, and so I signed off on the paper, but I ignored it because nobody thinks that the Earth was volcanically inactive early in its history. But then Kristen Manu, who's an astronomer at University of Toronto, wrote a paper in 2015 applying this to habitable zone planets, and he argued that many planets near the outer edge of the habitable zone might not be really as stable as Earth. They might get this limit cycling behavior. So that's a caveat to what I just told you. Here's a diagram of the habitable zone. So this is the ZAMS habitable zone zero age main sequence. This is from our 93 paper. The figure, though, is from Germany because I've got some German colleagues who are much better graphics artists than we were at the time. If you're going to draw a diagram like this is mass of the sun on the vertical scale and radius of the orbit in AU on the x-axis. You have to pick an instant in time because this habitable zone is moving outwards for all stars at different rates for different types of stars. What this shows you is that the habitable zone is relatively wide. So I'm going to define the boundaries in a minute, but unlike Hart, we find with our models, because we have this CO2 feedback in there, we find the inner edge in our model. This is the old 93 model, was at 0.95 AU, right, where Michael Hart had it. But his outer edge was at 1.01 AU. I mean, that's crazy, right? Because that's a 2% decrease in solar flux. The solar flux on Earth was 30% lower early in the Earth's history. So that just doesn't cut the mustard. So because of that feedback, the habitable zone is fairly wide. It's comparable in width to the planetary mean spacing, shown on a log scale here, right? So So there you have to know something about how planets are spaced in order to really estimate how frequently planets are going to be within the habitable zone. Most of this we don't know. We've been hearing at this meeting. That's one of the reasons we need these direct imaging telescopes.
The 1% makes sense if you think the Earth is only 8,000 years old.
Yeah, so that's right. Maybe that was Hart's bias coming in there, right? Okay, so what sets the boundaries? Eric's already talked about it a little bit. On the outer edge, it's if CO2 and water vapor are your main greenhouse gases, water vapor is just a feedback in the climate system, very powerful feedback. But see, the outer edge is set by CO2 condensation. In a 3D model like the ones that Eric was showing you, that would happen first at the poles. We do 1D models. I'm too old to have gotten into this 3D business. But even in 1D, you get two very important effects. The CO2 condensation changes the lapse rate in the troposphere. In the modern atmosphere, the meteorologists amongst you, if there are any here, know that that in the tropics, the lapse rate follows a moist adiabat, and there's also a moist CO2 adiabat where CO2 condenses out. And if you think about it, that reduces the greenhouse effect because it makes the lapse rate less steep, and so you get less greenhouse warming if you have a fixed stratosphere temperature. The other thing that is actually even more important is that CO2 is a really good Rayleigh scatterer. So if you get a dense CO2, it's about 2.5 times more effective at Rayleigh scattering than air is. And so if you get a dense CO2 atmosphere, the albedo of the planet goes up, even without clouds. So for instance, Venus has an albedo of 0.8, and that's always attributed to these sulfuric acid clouds that reflect the sunlight. But in our model, if you do Venus and you take out the sulfuric acid clouds, the albedo is still 0.6 because that's just the Rayleigh scattering from a 100 bar, 90 bar CO2 atmosphere. Right. So anyway, even in 1D, there's a limit to the outer edge of the habitable zone caused by CO2 condensation, and we call that the maximum greenhouse effect. It's really the maximum CO2 water greenhouse effect. On the inner edge, we already heard from Eric that you can get a runaway or a moist greenhouse from the positive water vapor feedback that Eric already described. The runaway greenhouse, the way I define it, that's when the oceans evaporate entirely. Our old limit for that was 0.85 AU. Then there's a moist greenhouse effect that Eric mentioned, but didn't really describe. The stratosphere can become wet, even if the ocean is still present on the surface. And then that allows water vapor to get up there. You can overcome the diffusion limit on hydrogen escape. And so you can lose the ocean while it's still sitting there at the surface. And in our old models, that limit was at 0.95 AU, right where Michael Hart had it. Since then, the absorption coefficients have changed. And this was something that was brought to my attention by a colleague, Colin Goldblatt, who's at University of Victoria. Most of the climate models today, almost all of them, use what's called the HITRAN database. I'm sure where's Eric? This is what's in the NCAR models, right? So HITRAN comes from the old AFGL tapes. It's a mixture of quantum mechanical calculations and a lot of laboratory observations, and it's very useful for doing Earth's climate. There's a new database called HITEMP. It's not that new now, it's been around for a while, but this is purely theoretical quantum mechanical, ab initio quantum mechanical calculations of absorption. And that can be done now to a much higher degree of precision than it used to be. And it turns out that if you do it that way, water vapor absorbs not just in the near infrared and far infrared, but all the way through the visible and into the near UV. And you can show that quantum mechanically. And it makes no difference for the Earth's present climate, so there's no reason to switch to that for the present day climate models. But if you're doing runaway greenhouses, where you get a lot of water vapor in the atmosphere, it's a big effect. And Colin showed that. This was a figure from his paper. This was on the right was our old albedo. We run these inverse calculations where we just run surface temperature up to where you get a very dense water vapor atmosphere, and we had a limiting albedo of about 0.35. clouds were at the surface on this. You can't do clouds very well in 1D. So that albedo was coming just from Rayleigh scattering in the atmosphere. And then if you look on the left, the top curve over there was the the old HITRAN database, which already had a lower albedo than we did. I should say, I was using band models back in 1993. This was before HITRAN was even out. But now with the high temp database, this pink curve on the bottom, I can't point at it. This curve down here is what you get with high temp, and the albedo, the asymptotic albedo is about half what we had. So that stabilizes the climate, or actually it destabilizes the climate. And so what happens then is that the moist greenhouse and runaway greenhouse now occur at about the same place. Manford put this figure up. This was Ravi Kaparapu, who was my postdoc for several years and is now at NASA Goddard. He and Ramses Ramirez, one of my graduate students, redid the old habitable zone calculations using, we derived a set of high temp absorption coefficients from high temp and redid the habitable zone calculations with essentially the same old model. And what happened, the outer edge didn't move much, but the inner edge moved right around the Earth. In fact, the model predicted once that the Earth was right on the boundary of the habitable zone. Well, that's not very satisfying because we don't really think the Earth's climate is that unstable. 3D models, though, solve this problem. And so, Eric mentioned the LMD model. This was a paper from LeConte et al., Nature in 2013. That's Francois Forget's group. What they pointed out in this paper is exactly what Eric talked about. It was first pointed out by Ray Pierre Humbert for the Earth's tropics. In the Earth's general circulation, you get rising air at the equator, and then you form these Hadley cells. And the descending air is very undersaturated because the water vapor rained out on the way up. And those undersaturated regions have low relative humidity, and you can radiate energy right out through them. So that, in this LeConte et al. Paper, they used the high temp coefficients with a 3D model, and that moved the inner edge right back to 0.95 AU, where it actually has been since Michael Hart's calculations. Eric, I don't know if I haven't read these more recent papers that you mentioned, but is 0.95 AU still good for?
Yeah, between several different models, between 3 to 5, 0.93 to 0.95.
Yeah.
Ballpark. Yeah.
There's surprisingly good agreement, actually. But there are researchers who don't trust the Earticians, basically. And clouds are a real problem, as Eric already mentioned. So we could be wrong about that. You can also define habitable zone boundaries empirically by looking at Venus, which doesn't look like it's been habitable for at least 1 billion years. Mars does look like it might have been habitable 3.8 billion years ago. And so if you put that in, then you can define a conservative habitable zone based on the climate model calculations and an optimistic habitable zone based on empirical calculations. And these are what are being used by to calculate eta sub Earth. So let me skip ahead here. I'm out of time, and you've heard much of this already. So I just want to mention direct imaging here, which has come up a couple times. HABEX and LUVOIR are these two mission concepts out of, there's 4 flagship missions that NASA is currently considering. 2 of them are direct imaging missions for exoplanets, although LUVOIR would be a big, space observatory for all astronomers. The other 2, I think, are the Origin Space Telescope, which is far infrared, and there's an X-ray LINX. Right, so those are the 4 mission concepts that are being debated by the Astro 2020 Decadal Survey. I really hope that either LUVOIR or HABEX or some amalgam of them will be picked, because that, as Eric already said, we're data starved in this field. And I'd love to see NCAR and HAO get involved in it, but they're going to need data too. So all of us that are interested in Earth-like exoplanets really need these missions. And when they do happen, I think there's just going to be a wealth of new information. And I hope to be still upright when all of that happens. So I'll just put these up and open it up for questions.